welcome to Teaching Grade 11 Physical Sciences. Today we are joined by John. Hello, John.
Hi, Helen. Good to be with you again.
It's always good to have you in the Mindset office or studio. And of course, we have Dylan behind the buttons. Hello, Dylan.
Hello, everybody.
And unfortunately, we're not coming to you live because we have had some technical difficulties. So that means you won't be able to tweet in. But you can still win prizes by submitting your resources to us through the email address competitions@digitalclassroom.co.za, and look out for the secret code displayed at the bottom. Put it in your subject line. We'll then make them all public and we'll choose some winners. You could win a phone or a tablet. Did you know that?
That's great, Helen, really. Yeah.
And not just a cheap tablet that you can get for R1,000. It's a proper Samsung Galaxy tablet. It's nice.
Very nice, very
Yes.
nice indeed. Yeah.
So they're waiting to be won. Submit your resources. Okay, John, we have had you before, but why don't you give us a brief introduction? Who are you and why are you here?
Okay, Helen, I'm a physical science teacher. I began teaching way back in 1987. I taught in various schools around the country, starting in Durban at the school that I went to high school at Durban High, Durban Boys High, and then moved on and started to slowly migrate to the west, go west, and moved up to Kersney College, St. Charles College, and then to St. Stithians Girls College. And that I stayed there until 2004. So I had about 17 years in the classroom. And in 2004, I joined Mindset on a full-time basis. I had been doing some work as a freelancer in the year before that. And so I have been associated with Mindset more or less since Mindsets began, and started as the subject matter expert or coordinator for physical sciences.
Yes.
And developed all sorts of classroom resources. And in the time that I've been at Mindset, the last 10 years, I've done various things and done some interesting stuff.
You've also done your, correct me if I'm wrong, your honours in...
Correct. So in 2007, I decided it was time to go back to university.
Yes.
And to update my skills. And I registered for a BSc Honours in Science Education at WITS.
Okay.
And did that over the 2 years and really enjoyed the challenge of going back to study.
Yes.
And found I appreciated it more than when I'd done education stuff directly after doing my BSc. So there was a whole lot of experiential learning that I had, and I couldn't necessarily put the right theory or the name to it.
Okay.
But in the course of doing my honours, I was able to confirm much of my belief about teaching.
Well, that is the great thing about studying further, isn't it?
Yeah.
But today we're talking about electromagnetism.
Yes, and it's a really inspiring topic. And although I think that as I think about this topic, don't necessarily do the traditional teaching approach to this topic. But I hope that what I share with you will be valuable and useful for the teachers out there. I wouldn't say that it's something that everyone will do,
yes,
but it's certainly something to reflect on.
Yes.
And so I hope that as we discuss the ideas, that people will engage with what we're saying and think about the way they're doing things perhaps differently.
Okay. Well, before we get on to all of this, why don't we take a look at the book I've been reading, which is Teach Like a Champion. And there are 49 actionable steps in this book. Today we are on step number 13, which is called Name the Steps. And the quote from the book says, "Champion teachers help their students learn complex skills by breaking them down into manageable steps and often giving each step a name so that it can be easily recalled." Now, thinking back on my teaching practice, I have taught some classes that struggle to understand, and this has been a way I've taught to help them cope with things they usually wouldn't have coped with. Reflecting on it, though, I know that they had no clue what they were doing. They knew how to get full marks in that question, that particular topic, but would they be able to apply it in real life? Never.
Well, it is an interesting point that is raised. I think that there is room in some situations to be teaching procedures and methodologies. But I also think that there is a danger in summarizing teaching of particularly maths and science just to a set of procedures.
Yes.
Because there's so much more. And that's part of what I really wanted to share with you in terms of this topic. Because in essence, there isn't a whole lot of content, but there are many teaching opportunities that are there for both the growth of the teacher and the growth of the learners.
I think it comes down to priorities. It's what is your priority? Do you want them to be able to complete this question, or do you want them to be able to think about this concept and create questions from their thoughts?
Yes, I think you're right in terms of that. I do also think that it's important if one breaks this down into a topic, and maybe this refers to a very narrow procedure. For example, plugging into the formula Faraday's law equation.
Yes.
And how do you solve for it? Well, what are the steps that you would do? Identify that you've got things in the correct units. Identify what the missing variable is, and then basically substituting and making sure that you've got your answer with the correct unit. And that might be a set of procedures. And one could teach even a weaker learner how to do that. But would they have understood what's actually happening? And probably they wouldn't.
Well, even applying the right-hand rule to see where the direction of the
magnetic field
is going, you could reduce that to a set number of steps.
Yeah. I'm not in favor of doing that for everything. I think it might have a use in terms of recall and helping learners. We use mnemonics, and we use all sorts of memory aids.
Mnemonics is when you create a rhyme to
or a word.
Yes.
That is an arbitrary arrangement of letters, and each of the letters of that word then give you some sort of meaning.
Okay.
So it sticks in your brain.
Yes, like BODMAS.
Correct.
In mathematics. Yes.
So those are some sort of things that I think might be similar. But I'm interested in that quotation more in the approach to learning. And I would suggest that there isn't one way of going from point A to point X or Z.
Okay.
I would suggest that there are many ways that learners could go to arrive at the same destination.
Yes.
But what I do think is important is for teachers to be the tour guide, to make it clear and explicit to the learners where they've started and where they're going. So if we're doing the journey on electromagnetism,
yes,
there are components of learning that one would go through, and one would need to reflect and say, well, we've got to this point, we now understand that, now let's go to the next step.
Okay.
And understand where we're going in the final analysis. So we want to explore the whole dimension, the link between electricity and magnetism, and we want to be able to solve all the problems and be able to explain and understand Faraday's law. So what are the steps of doing that?
Yes.
And I think there are many routes to getting that whole journey completed. But I do think it's of value for teachers in their classroom to tell learners the route.
So there's a transparency in your teaching.
Correct.
Okay.
However, and that might not only apply to electromagnetism.
Yes.
It could apply to any topic. To say we're here at the beginning,
yes,
and this is where we're wanting to get to. And this is the route we're going to follow, but we could follow another route, particularly if a learner who's engaging with the process asks a question, and you might need to go down the road less traveled.
Yes.
But then bring the learners back to say, okay, so we've explored that little avenue, that side street, but now we're getting back to the main journey.
I feel like I need to do the same thing over here now, because
okay, yeah, absolutely. I understand where you're at.
Yes, so we're talking about electromagnetism. Where has it come from?
Okay.
In terms of content knowledge, what do they need before they begin? And just a list.
Okay, so learners have explored in previous grades, even in primary school, the ideas of magnetism.
Yes.
So we understand what a magnet is, and we understand things about magnetic fields. And I'm not going to go into too much more detail about...
You need to be a bit bigger.
So let's just do that again. Is that big enough?
That's great. So magnetism.
And we've also done some things on electricity.
Okay.
And we recognize that could be static, or it could be within circuits.
Okay. And this would have been covered in all previous grades?
In previous grades. Some of this is covered in grade 11 as well.
Okay.
But the order isn't quite... I've forgotten for a minute what the exact order is, but clearly electromagnetism precedes some of this. So... there's an alternative, and I don't want to get stuck up on the order. Certainly a lot of electricity, electrostatics and circuits has been covered in grade 10.
Yes.
Magnetism is covered in grade 10. We're re-looking at the connection in grade 11. We've done some circuit stuff. We're coming on to doing the combination of electricity and magnetism. And what's the link between them? And so what's the teaching approach? Where do we start? What are the possibilities? What are the key ideas? These are the things that I think we need to talk about.
Okay. We need to... Yes, sorry, Dylan.
May I ask a quick question?
With pleasure.
So in the section, we're tying together multiple threads from magnetism and static and current, electricity. Would you say that this section provides an opportunity for teachers to recap some of that content?
Absolutely.
Is it important that everybody's on the same page before you begin? In other words, is it necessary for us teachers to do some sort of pre-testing to make sure that those key concepts that we need in order to proceed are there?
I think that's always a good practice. You know, a baseline assessment, and particularly what is the magnetic field around a bar magnet, is a very useful diagram that will come up in this section later. Representing that and drawing that clearly is important, because a lot of the section is examined through diagrams.
I would like to add to that, though, with baseline assessments, they're almost useless if you're not having immediate feedback. If you're doing a baseline assessment now and you're only marking it in a week's time because that's when you have time, what's the point in doing a baseline assessment?
Doesn't need to be formal. And one of the little things that I saw, which I thought was really great, in a classroom, and I can't remember exactly where the classroom was because I saw it on a video, was teacher asking a series of questions, and in this particular class, he or she had given each of the learners a slate.
Okay. Like
a chalkboard slate, and if you didn't have a chalkboard slate, it could be a piece of paper.
Yes.
And the kids just basically had to write up the answer and hold it up. So is it A, B, or C? Could put it on the overhead projector, and immediately by holding it up, the teacher was then able to see where the majority of the class was. And
That's
also
a
be able to identify the kids that didn't necessarily have the full concept.
Yes.
And for me, that always without picking on a group of learners, would elicit a discussion. So so we're going to do something there. What do you remember about magnetism? So, and you could do a whole series of those little questions and say, well, why do you say the answer is A?
Yes.
So all of you that said the answer, get in a group, explain. Well, you said the answer is B, Helen. Have you got any ideas why it's B? Or
It sounds like it would be a worthwhile activity to do for a full lesson,
Yeah.
discussing all previous concepts
I would agree.
in that manner.
It might not need a whole lesson,
Okay.
but I think it's certainly always a useful tool to find out where your learners are at. And that is part of that journey you want to take them on. Because if you don't know where the starting point is, where they're starting from 3 different, and they've missed the basic steps, then you're going to struggle to get them
Yes.
to the end point, the desired outcome.
Okay. Shall we take a look at your 3 pressure points for this section?
Okay, so
Okay.
let me.
The first one says converse thinking, and I know I joked earlier and I said, what are those converse all-stars? What do you mean by converse thinking?
Okay, so it's interesting that in Euclidean geometry,
Which they are
which they're doing more or
right
less
now.
at about the same time, they're doing a whole lot of stuff on circles
Yes.
and quadrilaterals. So you have a theorem, and you have the converse.
So,
So in a sense, it says if A, then B. What we could do is say if B, then A.
okay.
So it's a different starting point. And in terms of electricity and magnetism, learners really struggle with that, because the concept that we need to get to, and we'll expand on it a little bit more, is that historically we started with the idea that electricity or current, electric current, produces a magnetic field.
Okay.
And that was great, and it was a great discovery. But it didn't do much in reality. It has had some impact, and it's been very useful as a building block.
Okay.
But the real thing in terms of the breakthrough in popularizing electricity came when people started to say, could we do the reverse process? So if we started with a magnetic field, is it possible to take that magnetic field and do something to produce an electric current?
So you're saying the converse thinking that they struggle with is to flip that around.
Yes. And to recognize these are 2 processes that are related to each other.
Yes.
And in grade 12, it becomes even more interrelated, because the one process is used for making a motor, and the other is used for making a generator. But I don't want to get into that at the moment.
Yes.
Because that's another example of converse thinking. Because in a motor, you use electric current to produce motion. In a generator, you use motion to produce electricity.
Now, why aren't we teaching that at the same time?
It's a very good question, and I think it's probably because the maths isn't a problem in that respect, and alternating current is something that learners should be familiar with. We use it every day.
Yes.
But we do want to have some sort of progression, and the concepts involved, particularly here, this process is called electromagnetic induction. Is that going out of
Yes,
shot?
unfortunately.
Electromagnetic induction. Now, let me put it
Okay.
over here. It's known as induction, EM induction. So, are we okay with that?
Yes.
So this is quite complex, and learners do struggle with So instead of harping on it, because over here we're really just dealing with either a magnet moving or a single conductor, in this case a single conductor producing a magnetic field, or a solenoid. With a motor, you're dealing with two conductors in a magnetic field. So the level of complexity is greater. And I'm not sure that grade 11 learners are really academically mature enough to deal with that complexity.
Yes.
Because it is quite complex, because you've got movement, you've got rotation, you've got to be able to imagine things, because in most cases textbooks are showing things in 2D.
Well, they're
flat,
limited.
And they're limited, and they're not
Yes.
showing you motion. And so, although the exam type questions are quite limited in their scope, a full understanding becomes quite difficult. And I think they also needed to leave something for grade 12, to be honest with you. So that's converse thinking.
The next one, understanding magnetic flux.
Okay. So
flux is change, isn't it?
not really.
Okay.
Okay. So this one is a little more complicated. And so I don't think this is particularly well taught. But Faraday's law states that the induced EMF is directly proportional to the change in magnetic flux, or the rate of change of magnetic flux.
Okay.
The equation is written like this, as E equals minus N, usually, delta phi. The minus isn't always put there, and delta phi, being a strange letter, has a meaning where phi is equal to the magnetic field strength times an area times cos theta.
Okay.
And so you can see mathematically that's quite complex.
Yes.
And it's quite difficult for learners to pick up all the relationships.
Is this grade 11 work?
This is grade 11 work.
Okay. And it comes up in this section.
In this section. And the key point here is an understanding of what that expression means. This is magnetic flux. Okay.
Okay.
So can I try and break it down, because that's very symbolic.
Okay.
And what I'd like to do is to illustrate for you, which leads us on to the next point.
And the next point
Which
is
is-
working with symbolic diagrams and a subpoint using the right-hand rule.
Agree.
Okay.
Okay. So
Yes.
I'm going to come back to that little magnetic flux.
Okay.
It's usually only dealt with in textbooks that I've seen in the section under electromagnetic induction.
Okay.
But I believe that when we start to teach the relationship between electricity or electric current and magnetism,
Yes.
when we're doing the magnetic effect of electric current, we should at that point start to introduce to the learners the idea of magnetic flux. So may I illustrate for you for a minute?
Yes.
And at the same time, just work through the symbolic diagrams.
Now, are you saying that when they do magnetism in grade 10, you should start introducing this idea, or only this electromagnetism?
I think it's a grade 11 topic.
Okay.
But I think it comes at the beginning. And many people leave it only and teach it in isolation with electromagnetic induction. So there are two parts to this topic.
Okay.
There's the magnetic effect,
Okay.
which was being done in earlier grades as well. So if you wind a piece of wire around a nail,
Yes.
you can make an electromagnet. And that's the level of primary school or grade 9 or 8. We can make something magnetic using electric current.
Yes.
I think at grade 10 level, when we start to, grade 11 level, when we start to introduce them to symbols and symbolic diagrams, it's the ideal opportunity to expand that slightly at the beginning of the introduction and introduce them to the idea of magnetic flux.
Okay.
So let me try and kill two birds with one stone.
Yes.
And deal with that idea. So pretend for a moment that this is a conductor.
Okay.
And we're going to say this is connected to a battery.
Yes.
And at the moment, you're looking at it from a side-on view.
Okay.
So if I had to draw what you would see from a side-on view, you would see something like that.
Yes.
And we would, let's say for a moment, let's make this the positive end and make that the negative end.
Okay.
So from a side-on viewpoint,
And that's in terms of the current flowing.
from positive to negative.
Okay.
So we could have turned it up that way, but we're just looking at it from a side-on point of view. So
Yes.
we're looking at it at a side-on. So we're going to indicate the direction of current in that direction using an arrow.
Yes.
Now, what Ørsted found, the person that discovered this first link between electric current and magnetism,
Yes.
was that if you connected a conducting wire to a battery, in that case it was a series of cells, and they were wet cells, they were having chemical reactions, they were very big, and they were cumbersome, and they weren't very good.
Yes.
They didn't last very long either. But what he noticed was that if he had current passing through, and almost by accident, he had a little compass needle sitting over here with the compass pointing in a direction like that. And when he turned the battery, the switch on, he suddenly found, hold on, this is no longer moving that way. It's not pointing north, it's changed its direction.
Okay.
So instead of it pointing north, which is the global north, when he turned the current on, he suddenly found, whoops, what's happening? It's moving in a different direction.
So is that the magnetic flux that they
no,
deal with?
that's not magnetic
Okay.
flux yet. It's just the magnetic field that's affecting that compass.
Okay.
And I was just illustrating that.
Oh, okay.
So let's just be clear about it. Around this conductor,
Yes.
when there's current, there is a magnetic field.
Yes.
To establish the direction of that magnetic field, we use our right hand.
Okay.
And we will indicate with the thumb that the direction of the current. Okay? So
Okay.
as I'm holding it there, current is pointing in the direction of the arrow. My thumb is pointing in the direction of the arrow. The curl of my fingers gives the direction of the field lines. So the field lines are running around in a loop wise, round like that.
Okay.
Okay? And they're moving around so that if I placed my little my little compass needle, they would point in that direction, the compass needle. Now that's rather messy. Okay?
Yes.
Because we've got a three-dimensional thing that we've flattened into a two-dimensional drawing. And it could be quite confusing because we don't all use 3 colors to draw diagrams or 4 colors to draw diagrams. So the thinking was, let's not only do that sort of diagram because it's not complete, because it should go all the way around. So the first step was, instead of doing that, and I'm going to redraw that without the black lines crossing, the field lines crossing over, just going to put the symbols back. People decided that instead of doing it that way, let's start to develop a symbolic representation.
Okay.
And as you can see, there's a 3D, a circular magnetic field around here.
Yes.
So the idea was, well, let's not look from the side or from the top. Let's look from the ends. So if you imagined you put your eye over here, what would you see? And if you put your eye over there, what would you see? Okay?
Okay.
My eye is probably a funny eye, but anyway, you get the idea.
Yes.
So if we looked from the end, I think you would agree, looking end on at this object, you'd see a circle.
Yes.
So the conductor would be a circle.
John,
Yes.
I feel like we're getting quite deep into content here, and we're talking about teaching. So,
I'm coming to it.
okay.
So remember, we were talking about the complexity and the sticking point. And
Yes.
I said to you that one of the sticking points is interpreting this diagram
Okay.
and specifically explaining magnetic flux. And I just give me 2 minutes and I will finish this.
We've got those 2 minutes.
Okay, thank you. At this point, we would view it like that. Which way is the current going? It's going into the board. It's going away from me. So the symbol that we would use would be that.
Yes.
an arrow, like a dart, being thrown away from us. At this end, the observer would see the current symbol, meaning it's coming out. So this means in, and that means the cross means in and the dot means out.
Okay.
So if I wanted to represent the magnetic field now, it would be easier to show that this is a three-dimensional concentric circle around there. We use the right-hand rule, which is my third sticking point, because kids don't like or don't really know the difference between left and right.
Yes.
But if we use the right-hand rule, current coming out, thumb in that direction, magnetic field lines means that this is anti-clockwise. So it goes like that, like that. Whereas this one, current is into the page, into the plane, and the direction of the magnetic field is clockwise. Agree?
Yes.
Now, that's the traditional approach. And the approach is fine, and there's nothing wrong with it in teaching magnetic fields around single conductors or even around a solenoid, a coil. But I think that people miss a trick, because this symbol, this notation of in and out, doesn't only have to refer to current direction. It can also refer to the magnetic field direction.
Okay.
And so I want to go back to my original diagram and just show you, in showing you, explain magnetic flux. So we said that's the direction of current.
Yes.
Positive was on this side, negative was on that side. Right-hand rule. Agree?
Yes.
Right-hand rule. What is the magnetic field doing on that side of the conductor?
It's coming up.
It's coming up. So how would I represent that magnetic field using my convention?
With the dot.
With a dot. So a series of dots close to the conductor, and on this side, a series of crosses close together and close to the conductor. Okay? Now, that magnetic field changes with distance, and it becomes weaker.
And
So-
they do know this already, that magnetic fields
Change. Yeah, they know it from the bar magnet.
Yes.
So here we could spread those field lines further apart, and in a similar way we could spread those field lines further apart. And I might not be drawing it exactly right, but it gives you the idea.
Yes.
So it's not a uniform field. That's what I'm trying to illustrate here. This is representing a magnetic field around, in a region of space,
Yes.
around a conductor.
Okay.
Remember, this is saying this is current,
Yes.
this is the current, and this is the magnetic field.
So
Now-
you're saying the sticking point is the drawing of the diagrams.
And specifically understanding in and out,
Okay.
and applying the right-hand rule to this. But the more important thing is, because I don't think enough people teach it, is to understand the representation of what magnetic flux is.
Yes.
Remember, we had that formula of B times A times cos theta.
Yes.
What we need is to recognize that we've got to have an area through which the magnetic field passes.
Okay.
Okay. And the important thing here is that we want to find the angle between the normal to, and it's a crazy situation. The area has to be at 90 degrees to the field lines for them to be the maximum.
Yes.
So in that sense, that angle is important as well.
Okay.
That's where you get your maximum. And that's important for later in terms of machines and electrodynamics later. But what I like to do, and what I suggest teachers do, is to get this idea of the area. So if we had an area here, you could see that a number of field lines passing through this area, if it was the same size, would be smaller. The product of field strength and area would be different to that one, because you've got more field lines passing through this one.
Okay.
Does that make sense?
Yes.
Okay.
Okay.
So getting a visual representation.
John, we have 10 minutes left.
Oh,
Yes.
Helen.
I have to speed you
You
along.
have to speed me along.
Yes.
But I think we've covered a really important conceptual difficulty.
Good.
Okay. So I know that wasn't what was in our plan, but we started with the sticking points and we missed. So let's move on.
Yes. Let's go to your 5-point teaching strategy.
Because we'll rush through.
It starts with electricity in daily life.
Okay.
Yes.
Can I pick that up very quickly? So because electricity in daily life is such an interesting topic, and there's so many options that we can talk about, so many interesting things, I suggest to teachers to ask their learners to discuss and investigating what have I done with electricity today. And the basis of this question is part of a theory of, or a method, a way of thinking about teaching science, called Science, Technology and Society, or Society, Technology and Science, STS. We're finding a relevance to society and finding technology that has a solution that can impact, where science can impact society. So
it's making the content real to them within their situation.
Within their situation. Okay. And so exploring this idea, we can see that electricity, which might have ended up just being a stuffy theory of a couple of equations of no use to anybody, can have relevance. And it's pervasive. A lot of what we do is related to electricity.
It is possible to teach this section without making it real to everyday life, isn't it?
Yeah, it is.
So we can teach just those formulae
all in here and those diagrams, and
just plug and chug.
And we're just going through the steps, and there's no room for inspiration. There's no room for making the connection.
So that's what is different about this approach.
Absolutely. And I think that in the end result, what you're also wanting to do is impact society with science using technology. And there are a whole lot of possible activities that I'm sure we can talk about. Maybe not in this lesson, but maybe you'll include them in your blog.
Yes. The next one says the link between electricity and magnetism.
We've covered that to a large extent.
The converse thinking.
That's where that comes in.
Okay.
So I think it's really important that learners get that converse thinking. And they can inquire. So is it possible? Scientists struggled for a couple of years thinking about this, and it was a huge aim. So is it possible, and why is it important? If we skip on to the next, we find the solution.
Yes.
And for me,
the next one is the Faraday story.
The Faraday story.
Yes.
And I'm going to summarize it very quickly, because for me, it's about exploring backwards and saying, what's the nature of science? And how is science knowledge transferred, and how is it improved, and how is it developed? And for me, Michael Faraday stands as the epitome of inspiration in terms of science education, because he was a peasant, young boy, didn't go to school, started an apprenticeship at 8 or 9, earned money to pay for his family's food as a bookbinder, but he taught himself to read. And out of his reading, in any of his free time, he read the books that he had bound. And some of those were scientific journals. And he developed a passion for science. But the doors were closed for him to pursue, to become a scientist, because he wasn't born of noble birth. And so he could only eventually become a lab assistant. And at the time, the inquiry that was going on was, is it possible to use magnetism to make electricity? And it was through his experimentation that he found, by moving a magnetic field relative to a coil, you could induce a current. And that's where we got that fancy equation from.
Now, the inducing a current really is covered with grade 12 work.
It starts in grade 11. It is picked up again in grade 12.
Okay.
And it's important for us to understand that we can't just leave the grade 11 work and forget about it, because it's going to be essential to understanding motors.
So you can introduce this here and introduce it within, well, inducing a current and the importance of inducing a current in grade 11.
You have to.
So that you can build on it in grade 12.
Exactly. So the picture here that we want to get to is that if you have a coil, and my drawing isn't very good, so, and we've got a magnet, if you move the north magnet into the coil, what you will find is if this is connected in a circuit into an ammeter or a voltmeter, a galvanometer there, you move it in and out, you will get a reading on that. And that's where our generating capacity comes from.
Yes.
And so you can see how it links to society, because we no longer use batteries as our main source of electricity, we use generators. And that's Michael Faraday then went on to build motors and to suggest how to do a generator. And so he not only left it there in his thinking, but he popularized science and made it accessible to people. So he really is a role model of inspiration, that nothing is impossible if you really put your mind to it, work hard and go for your goals.
And it doesn't matter where you start either.
Doesn't matter where you start, exactly. We've covered a little bit of the representing the 3D.
That's the
because that
point.
was that was the fourth point. So I would tell Michael Faraday's story in a class.
Yes.
To motivate learners, to recognize it doesn't matter who you are and what your background is, you can actually succeed if you just apply hard work.
I think it also speaks a lot to pursuing the answer.
Yes.
It's got to find the answer to the question. If there's something that's bothering you, carry on
and
exploring
and
it.
explore it and don't give up. And electricity is full of that. Thomas Edison is another one who developed the light bulb. Out of 999 attempts, they didn't work, and on the 1000th chance, he managed to get an incandescent light bulb. I just want to move on to the next thing, because we've dealt with those diagrams and the magnetic flux, and the last one was just re-looking at the equation, where we said...
is this the investigating relationships?
Yes,
point?
investigating relationships. The EMF that's induced in Faraday's law, directly proportional to the rate of change of magnetic flux. And lots of learners struggle with that notation. I can't
imagine why. I mean, it looks perfectly normal.
So directly proportional, we've covered it so many times.
Yes.
But because this is a complex situation where you've got B times A times cos theta, it becomes a little bit where phi, sorry, not theta, where phi is that expression. Kids struggle with this.
Yes.
And it can become a recipe lesson. But I think it's so much easier if we begin to understand what this equation is saying. So it tells you if you move that magnet faster, if you reduce the time for the change in time, then you're going to have a bigger magnetic flux.
Now, let's say I'm teaching a class that really does struggle with scientific understanding and things like that. Would it be all right for me to introduce the importance of electricity and how it impacts our everyday life, and then teach recipe teaching? Plug and chug?
It's not ideal, because you do need to expand. And I suppose that in many cases people do that. But for me, it loses the passion, and you lose the sense.
So how can I cope with that class then? How can I...
Well, even with that class,
yes,
I think the story of Michael Faraday is the one that you want to stress. Even if they don't get this totally, the seed of teaching kids about life is more important than them being able to recall Faraday's equation. Because primarily as teachers, I believe we teach learners, we don't teach content. And understanding where learners are, and in motivating them and inspiring them to achieve the best they can achieve, is probably more important than them spending hours on this and never getting it right.
You actually need a moment to let that settle. Teach learners versus teaching content. I suppose if you're teaching content, you're trying to get learners to mold around a formula and plug and chug and get the formula right. If you're teaching learners, It's a different way of looking at it.
It's
isn't
absolutely different, because you're recognizing there's Johnny who might come from a broken home, who might have had a whole lot of issues, or who might have a whole lot of misconceptions. And you're needing to facilitate and draw him out and inspire him and say, there's a future for you. There's something that you can be good at.
Yes.
And the world needs you, because you might be the Michael Faraday that's going to invent the next breakthrough in technology that's going to change the world.
Almost a why not you
Exactly.
type of attitude.
Absolutely. And don't let learners write themselves off. No, I can't. No, you can.
Okay.
I hope that's given us food for thought.
It has indeed. And we are at the end of our time. So thank you for joining us, John.
It's been an absolute pleasure.
And thank you for joining us, Dylan, and pressing all the buttons. And we'll see you again next week. Goodbye.
Created using